me show you something peculiar about light, something that's going to bother you. Take an ordinary pane of glass, a window, nothing special. Shine light at it. What do you observe? Most photons pass straight through, that makes sense. But not all of them. Some turn around, about 4 in every 100, 4% reflection. Now here's the question that should trouble you. Why those particular 4? You send 100 photons, completely identical, hitting the glass at exactly the same spot, same angle, same everything. 96 continue through. 4 reverse direction. What determines which ones reflect? Maybe you're thinking there are tiny defects in the glass, microscopic bumps that catch certain photons and send them back. That would explain it, wouldn't it? Except it doesn't work that way. You can prepare glass so pure, so perfectly smooth at the atomic scale that there's nothing for photons to bounce off, and you still get 4% reflection every time. All right, so perhaps individual photons are different from each other in some hidden way. Maybe they're spinning or vibrating or carrying some internal property that determines their fate when they hit glass. Sounds plausible, until you see what happens next. Now, take a thin sheet of glass instead, a film. This gives you 2 reflecting surfaces, front and back. Simple reasoning says if the front reflects 4% and the back reflects 4%, you should get roughly 8% total. Basic arithmetic. But watch what actually occurs. Change the thickness of that film, and the reflection percentage changes dramatically. Make it 1 thickness, you get 0 reflection. None. Make it slightly thicker, you get 16%. 4 times what you started with. Same material, same light, only the thickness changed, and the reflection swings from nothing to everything and back again. This makes no sense. How can the back surface, which the light hasn't reached yet, affect what happens at the front surface? How does the photon at the front know how thick the glass is before deciding whether to reflect? Make the film even thicker, and this pattern continues. It cycles through 0, maximum, over and over. You can measure this oscillation for millions of repetitions. It's not an accident. It's not measurement error. This is fundamental behavior. So what's the explanation? The only one that works, and believe me, I spent years trying to find something better, is this. Light doesn't choose a single path. When a photon approaches that glass, it doesn't make a decision about reflecting or transmitting. It does both simultaneously, and not just both, it does everything. Every conceivable path through and around that glass happens at once. Now I can see you thinking, that's absurd. When I make a measurement, I get one answer. The photon either reflected or it didn't. And you're absolutely right about what you measure, but between emission and detection, something stranger is happening. Let me introduce you to what I call probability amplitudes. For every path light could take, there's an associated arrow. A little vector with a direction and a magnitude. These aren't metaphors. They're mathematical quantities that determine what you'll observe. When multiple paths lead to the same outcome, you combine their arrows. If the arrows align, pointing roughly the same direction, they amplify each other. The probability of that outcome increases. If the arrows oppose each other, pointing opposite ways, they subtract. They can cancel completely. The probability drops to 0. This is what's happening with that thin glass film. Light reflecting off the front surface has 1 arrow. Light traveling through the glass, reflecting off the back surface, and coming back out has another arrow. When the glass has just the right thickness, these 2 arrows point in the same direction. They reinforce. You get 16% reflection instead of 8. Change the thickness slightly, and now the arrows oppose each other. They cancel perfectly. 0 reflection. The 2 paths destroy each other through interference. This isn't limited to glass. Every optical phenomenon works this way. The blue color of the sky, the rainbow after rain, the shininess of metal, the transparency of water. All of it emerges from these arrows adding and subtracting, and the theory makes predictions that match experiments to extraordinary precision. 12 decimal places. That's like predicting the width of the entire North American continent to within the thickness of a single hair. Yet if you ask me why nature uses these arrows, why probability works through this interference mechanism, I have to tell you honestly, I don't know. Nobody does. We've been asking that question for decades. Nature simply behaves this way. Consider an ordinary mirror. You learned a rule in school. The angle of incidence equals the angle of reflection. Clean, simple. And it works. But why does it work? What enforces this rule? The usual explanation is that light travels in straight lines and bounces elastically like a ball off a wall. But that's not the real story. Light reflects from every point on that mirror's surface. Not just the center where the angle looks right. The entire mirror participates. Top edge, bottom edge, every spot in between. Each part sends light toward your eye. So why don't you see reflections coming from weird angles off the edges? The arrows again, light bouncing from the center region of the mirror, all travels similar distances. The arrows associated with those paths align. They add up constructively. That's what you see. But light from the edges travels very different distances to reach your eye. Some paths are much longer than others. The arrows spin around, pointing every direction. One contribution points up, another points down, another sideways. They cancel each other out. The edge of the mirror is reflecting light. That reflection is real, but the contributions from different parts of the edge interfere destructively, and you don't detect anything. You can actually prove this, modify the mirror, remove portions of the surface in a precise pattern, keeping only the regions where arrows would align. Suddenly the edge behaves completely differently. Light reflects at impossible angles. This is how a diffraction grating functions. It's a mirror with most of the surface removed strategically, so the usual cancellation can't occur. Light doesn't follow the reflection law because it knows the rule. It explores all possibilities. The law emerges from the mathematics of interference. The same principle explains something else that's always puzzled people. Why light bends when it enters water. You see a straw in a glass of water. It looks broken, bent at the surface. The light coming from the underwater part of the straw changed direction when it left the water and entered the air. We have a rule for this, Snell's law. It tells you exactly what angle the light will bend to, and it works perfectly, every time. But why does light follow this rule? How does it know to bend at that precise angle? The usual explanation is that light slows down in water, and somehow because it's slower, it has to change direction. But that doesn't really explain anything. That's just describing what happens without saying why. Here's the real answer. Light doesn't know about Snell's law. It doesn't calculate angles. It doesn't decide to slow down and turn. Light takes every possible path through the water. Straight paths, curved paths, paths that bend the wrong amount, paths that don't bend at all. Every conceivable route from the underwater object to your eye. Each path has its arrow, and most of these arrows cancel out. The paths where light bends too much interfere destructively with paths where it doesn't bend enough. They eliminate each other. The only paths that survive, the only ones where the arrows add up constructively, are the paths that follow Snell's law. That particular angle of bending is where the interference is constructive instead of destructive. The law emerges from the mathematics. It's not imposed on light from outside. It's a consequence of light exploring all possibilities and the arrows doing their addition and subtraction, and you can verify this experimentally. If you set up conditions where some of those paths are blocked, where the usual cancellation can't occur, light suddenly appears at angles that should be impossible according to the simple rules. Every optical rule you learned, reflection, refraction, focusing, all of it comes from the same underlying principle. Light explores everything. The rules are just descriptions of which paths survive the interference. Now let me tell you what's really happening when light interacts with matter. Because once you understand this, everything else falls into place. In the entire universe, when it comes to light and matter interacting, there are only two types of particles that matter. Just two. Photons, which are light particles, and electrons, which are the parts of atoms that do the interacting. That's it, two players. And these players can do exactly three things, three fundamental actions. Nothing more. First, a photon can travel from one location to another. It propagates through space. Second, an electron can travel from one location to another. Same idea. Third, an electron can emit a photon or absorb a photon. That's the interaction. Three actions. the complete list. Everything you see around you, every color, every shadow, every reflection, comes from these three actions combining in various ways. When you look at a red flower, photons from the sun arrive and hit electrons in the flower's molecules. Those electrons absorb the photons, move around, and emit new photons. The red ones get emitted preferentially because of the specific electronic structure of that molecule. Red photons travel to your eye, get absorbed by electrons in your retina, trigger a cascade of events. Every step is just those three actions repeating. Photon moves, electron moves, photon gets emitted or absorbed. Now each action has a probability amplitude associated with it. An arrow for a photon traveling from here to there, there's an arrow. For an electron traveling, there's an arrow. And for the interaction, when an electron emits or absorbs a photon, there's an arrow too. The arrow for that interaction is always the same magnitude, always. It's a number close to 0.1. If you square it to get probability, it's about 1%, 1 in 100. This number determines the strength of all electromagnetic interactions. It controls how atoms hold together. It sets the scale for chemistry. It appears everywhere in the theory. And where does it come from? Nobody knows. You can measure it incredibly precisely. It's approximately 1 divided by 137, about 0.0073. We call it the fine structure constant. Why that value? Why not something else? There's no answer. It's just a fact about our universe, a number we measure but cannot explain. Here's how you figure out what happens in any situation involving light and matter. You draw diagrams, simple pictures showing all possible ways events could unfold using those three basic actions. A photon travels here, hits an electron, the electron moves, emits another photon, that photon goes somewhere else, every conceivable sequence. For each diagram, you calculate its arrow by multiplying together all the individual arrows for each action. Photon travels, multiply by its arrow. Electron travels, multiply by its arrow. Interaction occurs, multiply by that number, about 0.1. Each time there's an interaction, you multiply by 0.1. So a diagram with one interaction contributes about 0.1 to the total. Two interactions, 0.01. Three interactions, 0.001. The more complicated the sequence, the smaller its contribution. This is why we can make predictions at all. The simplest diagrams dominate. The complex ones contribute tiny corrections, but you can't ignore all the complicated diagrams. Each one adds a small adjustment. When you include thousands of these corrections, the predictions match experiments to 12 decimal places. No other theory in science achieves this precision, not even close. And here's something remarkable. In these diagrams, photons can do things that seem forbidden. They can travel backward in time, move faster than light, carry negative energy. These are virtual photons. They exist only as intermediate steps in the calculation. You never observe them directly. One electron emits a virtual photon. That photon does something impossible. Another electron absorbs it. The final result is just two electrons repelling each other. You never see the virtual photon, and you must include these impossible paths. If you calculate only the sensible-looking diagrams, you get wrong answers. The theory only works when you allow photons to violate the rules temporarily, even though the final answer always describes something perfectly reasonable. This is what I mean when I say nature is peculiar, not random, not chaotic, just deeply, precisely strange in ways that give exactly correct predictions. Let me tell you about one of the most precise tests ever performed of this theory. There's a property of the electron called its magnetic moment. It's like the electron is a tiny magnet, and the theory predicts exactly how strong that magnetic field should be. The calculation is extraordinarily difficult. You have to draw thousands of diagrams, include all the complicated paths, account for virtual photons doing impossible things, add up millions of tiny contributions. When physicists did this calculation in the 1940s, it took years of work, enormous tables of numbers, calculations done by hand because computers didn't exist yet. And when they finally got the answer, they measured the electron's magnetic moment experimentally. The theory and experiment agreed to 8 decimal places. 8. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. Since then, the calculations have gotten more sophisticated. The experiments have gotten more precise, and the agreement has improved. Today, theory and experiment match to 12 decimal places. 12! No other theory in the history of science has achieved anything close to this level of precision. General relativity, Einstein's theory of gravity, tested to maybe 4 or 5 decimal places. Newtonian mechanics, maybe 6 decimal places in the best cases. This theory of light and electrons, 12 decimal places, and there's no sign of disagreement, no hint that it's breaking down. People have looked for cracks, for places where the theory might fail, for energies or distances or conditions where the predictions go wrong. Nothing. It works everywhere we can test it, and yet we still don't understand why it works. We can calculate with incredible precision. We can build technology based on these principles. But the fundamental question of why nature uses these rules instead of some other rules remains unanswered. That's the strange position we're in. Perfect predictive power, no deeper understanding. Now we come to the uncomfortable part. The part where I have to admit what we don't understand. Why these rules? Why does the interaction strength have that particular value? Why do the arrows combine the way they do? Why does probability come from squaring the amplitude instead of some other operation? I don't know. Nobody knows. These questions have persisted for decades. Many brilliant people have wrestled with them. The theory works. It's the most successful theory humans have ever created. But understanding why it works, that remains elusive. There's a certain honesty required here. Science isn't about pretending to have all the answers. It's about being precise about what we know and clear about what we don't. We know how light behaves. We can calculate it with extraordinary accuracy. Why it behaves that way, that's still mysterious. Maybe someone will figure it out, eventually. Maybe the answer is waiting in some equation nobody has written yet. Or maybe some things just are the way they are, and asking why is like asking why 3 is an odd number. It just is. But until we know for certain, we keep testing, we keep calculating, we keep pushing the precision higher, looking for any crack in the theory that might reveal what's underneath. So far, no cracks. Just this strange, beautiful picture of light exploring every path simultaneously, and the mathematics somehow always producing the right answer. Let me bring this together. We started with a simple question. How does light work when it hits glass? The answer turned out to be that light explores every possible path. It doesn't choose, it doesn't decide, it does everything simultaneously. And the interference between all these possibilities determines what we observe. Then we went deeper. All interactions between light and matter reduced to 3 basic actions. Photon moves, electron exchanges, photon. That's complete. These actions combine according to rules involving probability amplitudes. Little arrows that add and subtract in ways that predict nature with perfect precision. When you truly grasp this picture, you realize something unsettling. The world we experience, the world of solid objects and definite events, emerges from something much stranger underneath. At the quantum level, there are no definite outcomes before measurement, just amplitudes, just possibilities superimposed. The classical world we see is what you get when countless quantum events average out. This isn't a limitation of our knowledge. As far as we can determine, this is the bottom level. The arrows and the interference and the probability, that's what reality actually is. Some people have searched for hidden variables, some deeper mechanism that would make everything deterministic again, like classical physics was. They've looked for nearly a century, performed incredibly clever experiments, and every time the answer is the same. There's nothing hidden. The randomness is fundamental. The probability is built into nature. That's the toolkit for every optical phenomenon in existence. It explains everything from the colors of a sunset to the precision of a laser. But underneath the math, the mystery persists. Why these rules? Is there a deeper logic we're missing? The truth is, science is a work in progress. It's an unfinished story where every answer just reveals a deeper question. Think about it. In just 100 years, we went from discovering light particles to predicting their behavior with nearly perfect accuracy. It's pure magic disguised as physics. The universe is incredibly strange, but piece by piece we're starting to figure it out.